Greg Susana, Robert Simkus, and Andy Ackerman. We have recently finished a study where we have showed that latest semi-eclipse models still have problems representing clouds and radiation. And this brings me back to my PhD research, where I was working towards an improved treatment of cloud radiation interaction in weather and climate models. So today I'm actually going to present what I was doing as a PhD student at the Meteorological Institute Munich, together with my advisor, Bernhard Meyer, because I will likely build upon this research at some point in the future. So as a starting point, I want to mention Project Waves to Weather, which funded my PhD studies. It's one of the major German research projects in the field, uniting multiple universities and multiple scientists in the field of numerical weather prediction. And I was working on a project entitled Radiative Heating and Cooling at Cloud Scale and its Impact on Dynamics, where we have tried to better understand and ultimately improve the parameterizations of cloud radiation interaction in weather models. So in this project, it was obviously all about the weather, but this calculation of radiative transfer in a cloudy atmosphere is also a common problem in climate models, obviously. And so I will start with a very simple introduction about the interaction between clouds and radiation, how does it work in a real world, and how it's represented in numerical models. And then I will tell you few key findings and basic main concepts discussed in these 3 research papers. So I would start with this introduction slide showing the beauty of versatile cloud types and at the same time the complexity of real 3D interaction between clouds and radiation occurring in a real world. So when we talk about atmospheric radiation, we usually distinguish between solar and terrestrial radiation. And as radiation propagates through the atmosphere, it interacts with the medium, particularly with clouds. So clouds strongly modulate radiative field because they absorb, scatter, and emit radiation. And this is a highly 3D problem, obviously. These 4 photos were taken at different parts of the globe, different times of year. We see different types of surfaces which reflect and absorb radiation reaching the ground in unique ways. And all this suggests that this is indeed a complex problem in nature. But even if we look at a single cloud type over some local area or a shorter period of time, we see a lot of variability. And so in my family, we have a hobby called paragliding, and these 4 pictures on the right were taken during a 4-hour paragliding flight, and we see how quickly clouds change. They grow, liquid water content builds up, and they change their shape. And so the bottom line of these 2 introduction slides would be that clouds, as you all know, are highly variable, both spatially and temporally, and this is what makes them difficult to model, and consequently this is one of the main problems when you want to parameterize cloud radiation interaction. You would often hear people say radiative transfer theory is well known, well established, but one of the key limitations is the unknown input, particularly related to clouds. And so let's now quickly summarize how do we compute radiation in the first place. So this is radiative transfer equation, which describes all these basic processes: absorption, scattering, and emission. It's equation for the primary radiation quantity called radiance, and from that we can easily derive radiative fluxes and radiative heating rates. These are the 2 quantities that radiation scheme has to compute in a weather and climate model. So in particular, radiative fluxes at the surface, they are important for proper evaluation of surface energy budget, and a radiative heating rate distribution within the atmosphere is like a source term for prognostic temperature equation. Now this is quite tough equation to solve, but exact solutions exist, but they're computationally too expensive for operational usage in weather and climate models, and therefore another major challenge is really how to derive computationally efficient solutions. So therefore, we have to simplify the problem in many ways, and the central assumption that's employed obviously in all GCMs, but also NWT models and in most LES models is the independent column approximation, where we solve radiation in each vertical column independently of its surroundings. And in this way, we neglect horizontal radiative energy across the model domain. And then let's now take a look what's going on within a single column. I first assume that this column is cloudless. I fill the column with typical optical properties of background atmospheric gases, and I performed a simple calculation in solar particle spectrum for overhead sun, and I got this black curve. So solar heating rate of about 1 to 2 Kelvin per day, mainly due to absorption of solar radiation in the background water vapor. And in the second step, I have filled the region of this column between 1 and 2 kilometer height with typical optical properties of a water cloud, and I repeated the same experiment. And I got this blue curve. So we see we have this strong solar heating rate up to 40 Kelvin per day in this region where a cloud is located. And this is due to absorption of solar radiation in cloud liquid water, so droplets are highly absorptive. And this experiment really nicely demonstrates how large is the effect of cloud on the vertical profile of radiative heating rate. But clouds are not always so beautifully confined to a single column. And let's now look at the implication of this ICA as a function of model resolution. So how do we compute how such clouds interact with radiation as a function of model resolution? If we first assume that the cloud is resolved, it would look something like this. So different gray shadings represent different values of cloud optical thickness. Clouds are usually optically thicker in the center and then thinner as you go towards the edges. And when we compute the 3D radiation, when we perform this 3D radiation calculation, which we can afford for research purposes on such result cloud fields, it looks something like this. So our photons are able to propagate throughout the entire domain in all directions. And in the associate 1D radiation calculations, the photons are trapped to each individual column. First of all, I want to say there are multiple ways how you compute this radiation within individual column, but one way how to imagine this 1D approximation is that we only employ vertical radiative fluxes. So this scheme shows the radiation propagating vertically downward through the atmosphere, but we also have component of radiation propagating vertically upward through the atmosphere in this 1D computation. We don't have any horizontal radiative fluxes. And obviously, if we place these two images side by side, we can easily conclude that our 1D calculation is biased relative to the 3D benchmark, and this bias or error stems from neglected horizontal photon transport if the cloud is resolved. However, in models with limited resolutions, such as already in regional models with grid spacing between 1 and 5 kilometers, such cumulus cloud would be unresolved, and it would be represented like this in a regional model. So it's such series of horizontally homogeneous layers of partial cloudiness, where it's typically assumed that this partial cloudy layers overlap maximally in the vertical direction. And the only information that we have about the cloud field in each vertical layer is described with two parameters. So C, the cloud fraction, and average liquid water content. And when we perform the 1D radiation calculation on such unresolved clouds, it's now a bit different than before. It's a bit more sophisticated because we have to kind of steer radiative fluxes and divide them between the cloudy and cloud-free parts of model column. But we still don't have any horizontal radiative fluxes. And so when we compare this 1D calculation with the same benchmark as before, we see that we now have another problem. So in addition to this error stemming from neglected horizontal photon transport, we get another error source which stems from poor representation of unresolved clouds. And the relative contribution of these two error sources obviously depends very much on the grid spacing, on this delta X. So in global climate models with very large grid spacings, the poor representation of unresolved clouds would be the dominant error source in this case. But as you decrease the grid spacing down to the scale of global NWP models or regional NWP models, clouds get better and better resolved. And when I started my PhD, it was not clear which of these two error sources is dominant at the scale of regional models. And this was actually what I investigated in the first research paper, where we have quantified the radiative biases for such evolving shallow cumulus cloud field that you see here. And we have quantified these various bias sources. I've performed all radiation calculations with Libratron software. Libratron is library for radiative transfer. So it's simply a tool which allows you very accurate computation of radiation for a variety of atmospheric setups. And the main advantage of this software is the accurate 3D radiation model, Monte Carlo model, which we used as benchmark. At the time when I started my PhD, we didn't have a method which would be representative as a regional model radiation scheme, and therefore, as a first task, I coded this method. It's called the delta Eddington two-stream method with maximum random overlap assumption for partial cloudiness, for those of you who are more familiar with radiative transfer theory. So it's the method that was employed in German regional weather forecast model, Cosmo-D. But the similar approach is employed also in other regional models. And then I could quantify these biases as a function of various parameters listed here, such as the solar zenith angle, which obviously plays a huge role, surface albedo, shortwave surface albedo, and then also parameters which describe cloud width itself, such as cloud cover and liquid water path. And this is a very detailed sensitivity study. I wouldn't go into details here. I just want to tell you, like, the main conclusion was that even at this resolution of regional models, actually the poor representation of unresolved clouds seemed to be a larger problem than neglected horizontal photon transport. There are of course situations where also horizontal photon transport plays an important role, such as at low sun angles, at smaller values of cloud cover. But generally, yeah, so if you want to really efficiently reduce biases in regional models, you would need to find a solution how to take into account both these problems. Yeah.
So your two central things you're interested in, do they tend to offset those errors offset each other or exaggerate each other?
Depends. So sometimes they offset each other, sometimes they exaggerate each other. It really depends on the solar, on the spectral range, on the cloud cover, on the position within the cloud layer. Usually, I had like large plane parallel bias on the top part of the cloud layer, and then 3D effects in the shortwave at least came from the reflection of radiation from the ground, and then this radiation was being reabsorbed in the cloud layer, in the bottom part of the cloud layer. So I had like 3D effect at the bottom part of the cloud layer and large plane parallel bias at the top part of the cloud layer. We have looked at this study, we have looked at the vertical profiles in the cloud layer, also at net surface fluxes. So in the long wave, the plane parallel bias was the dominant error source in the cloud layer, and this was also the same for overhead sun in the short wave. But at low sun angles, 3D effects were dominant. Yeah. So, but still, yeah, surprisingly, also this 2.8 kilometer grid spacing, this was the former resolution of Cosmo-D, this biases stemming from poor representation of unresolved clouds were generally larger. And therefore, in the second part of my PhD, I wanted to find a solution which would at least partially eliminate these biases. And the basic idea for an improved treatment of unresolved clouds in radiation schemes, which are largely built upon, is called Tripleclouds. which was primarily introduced by Schonk and Hogan. And the underlying concept of this method is as follows. So instead of representing cloud in each vertical layer with a single homogeneous region, we now have two regions to represent the cloud in each vertical layer. So one region is used to represent the optically thicker part of the cloud, which I placed in the interior, and the second region then represents the remaining optically thinner part of the cloud. The third region in the layer then represents clear sky. And so the main challenge for me was then to couple radiative fluxes into such system of three-region atmospheric layers, and we will soon take a look into this problem in a bit more detail. But let's first try to justify our assumption. So here I took shallow cumulus cloud field case study, which you can see on the left, and the middle image shows the situation when you impose cloud mask into this cloud field. So white color denotes clouds, black color denotes clear sky. And you see that this cloud field has a cloud cover of about 50%. The right image shows vertically integrated optical thickness and highlights only optically thicker regions. And you see by comparing these two images that these optically thicker convective cloud cores are indeed located in the interior of individual clouds and are surrounded with regions of reduced optical thickness. And this is something that is supported by further LES studies. It's also supported by observations. It's also, the basic explanation for this is that in the interior, you often have stronger updrafts, which are able to sustain larger amount of cloud condensate. And then at cloud edges, you have downdraft motion and also turbulent mixing with the surrounding clear sky air, which is drier, and consequently cloud edges are thinner. Okay. So now we can go back to this basic concept of the Triplecloud scheme, and we can try to imagine such individual model layer divided into three regions. I'm denoting the two cloudy regions with K and Cn, so cloud thick and cloud thin. And it's important to keep in mind that in a host weather or climate model, we only have the information about the entire layer cloud fraction C. And so I, as a developer of radiation scheme, have to decide how to split this cloud fraction into two parts. And this is how I formulated the split with the aid of this alpha parameter, where I have said simply part of layer cloudiness is optically thick and the rest is optically thin. And we will talk later what's the optimal value of this alpha parameter. And now we can couple radiation into this triple cloud model. And this scheme shows the transmission of radiation through two adjacent model layers with different cloud fraction. You see, I had to distinguish between four different geometries, four different cloud arrangements. I have case 1 and case 2, depending on whether the cloud fraction in the layer above is larger than in the layer below. And then each of these two cases have two subcases, A and B. I wouldn't go into details here. I just want to tell you that I had to divide these fluxes between different regions in accordance with the sizes of individual regions. And based on this scheme, I have derived this table of overlap transfer coefficients. You see we have 9 coefficients, which describe what portion of radiation from each of the 3 regions in the layer above flows in each of the 3 regions in the layer below. And then we have 4 different cases, and finally I have derived a general formulation shown in the rightmost column. So if I go back to the previous slide for a second, with this S we typically denote direct solar radiation beam. But in the same way, I have also imposed diffuse radiation into this model. So one component of diffuse radiation which flows through such atmosphere from the top of the atmosphere till the ground, and then another component of diffuse radiation which propagates through the atmosphere from the bottom to the top of the atmosphere. And so for those of you who are more familiar with radiative transfer theory, this is the underlying two-stream framework in this case was the delta Eddington two-stream method. And then I retained the classic maximum random overlap assumption for the entire layer cloudiness. So for the sum of optically thick and thin cloudy regions. And I additionally employed the same overlap assumption for the optically thick cloudy regions. So this delta Eddington two-stream method, this is approach which work well for horizontally homogeneous cloudy layers. But as soon as you have partial cloudiness in the radiation scheme, you have to introduce an assumption how this partial cloudiness overlaps in the vertical direction, and this is this classic maximum random overlap assumption. But now that I have added an extra cloudy region into the radiation scheme, I also have to extend the overlap assumption, and this is what I did here. And this solver is also now implemented in LibreTrend and is freely available for everybody to use. But before I could actually apply it, there is one more thing that we have to think about. And so our next question is how to generate a pair of liquid water content values from the mean value, which is available in a weather and climate model. And similar as we have said before that we have to split the single cloud fraction into two components, we also have to generate a pair of liquid water content values characterizing the two cloudy regions. And in a very simple configuration where we simply have the layer cloudiness, or simply divide the layer cloudiness into two equal parts, we can write this mass conservation law as shown here on top right. So we definitely want to conserve the mass of liquid droplets within the layer when we do the split. And then a very simple way of generating a pair of these values is simply by adding and subtracting one standard deviation from the mean value. Since this is typically not known in a host GTM, we have to somehow parameterize it. And we often work with this non-dimensional parameter called fractional standard deviation, which is simply standard deviation divided by the mean. This is a simple measure of,
Why would you conserve mass instead of opacity? Opacity seems like the important thing that you care about, not liquid water content. That's cloud microphysics and all that. You care about radiation. So, just surprised.
Okay. What would be the difference if I would?
Well, if they have different effective radius, then that would be a different rule.
Mm-hmm. Yeah, here I have decided for liquid water content values, and then I have assigned the effective radii following some parameterization of Boglario, which, I could try it out. I did not have time to think about it, what would be different if I would play with optical thickness here instead of liquid water content directly. So this simple approach is something that I adopted from Schonk et al. And this was convenient for me because I had this, various estimates of fractional standard deviation of liquid water content, which I could use. I'm not sure if there are obviously also probably estimates of inhomogeneity of cloud optical thickness, but I largely follow the work of Schonk et al. And then
optical thickness is a lot easier to retrieve than liquid water content.
Thanks for this comment. Yeah. So I worked like that, and Schonk et al. Study from 2010 derived a global estimate of this parameter, which is 0.75 plus minus some uncertainty. So in this study, they considered various cloud types over oceans, over continents, in winter, in summer, low clouds, high clouds. It's really a global estimate. They've probably also included study where they have had estimates of cloud optical thickness, but they were converting these various parameters of cloud inhomogeneity to a single value. So, and then in the basic my basic experiment, I simply use this mean value as a starting point in this equation to generate a pair of liquid water content values in each vertical layer containing cloud. This is what I could use as input for Tripleclouds. So then I could finally test the scheme on such shallow cumulus cloud field case study. And I was always evaluating it against the 3D benchmark computation on the highly resolved LES cloud field. That's the best what we have, right? And then to put this Tripleclouds experiment into a broader context, I performed 2 additional calculations. So one was the traditional GCM experiment on this homogeneous layers of partial cloudiness. We wouldn't want that Tripleclouds gets worse than that, right? Then I also performed this full ICA experiment on the original LES cloud field, retaining the full cloud geometry, the full PDF probability density function of liquid water content. So I hope it's clear. I took this LES cloud field, I calculated 3D and ICA on this LES cloud field, and then at the end I horizontally averaged the heating rates to obtain a single vertical profile through this scene in these 2 experiments. But then in order to create a proper GCM experiment, I first averaged the cloud field horizontally to mimic this poor representation of clouds in GCM. So I computed this average liquid water content profile and cloud fraction, and I ran the GCM radiation solver on this profiles, the delta 18.2 stream method with maximum random overlap assumption for partial cloudiness. And then I employed the splitting methodology that we've talked about before to generate the pair of liquid water content profiles characterizing this optically thin cloudy region and optically thick cloudy region from the mean liquid water content value, as if I would need to do in a GCM. So let's see what we get. This is the root mean square error within the cloud layer for these various experiments. I performed different calculations in solar part of the spectrum for different solar zenith angles, in the thermal part of the spectrum, and finally I'm showing the error of total heating rate during daytime sum of solar and thermal radiation. And yeah, Tripleclouds worked really well in this case. I was really happy with this result. So the traditional GCM bias was reduced by a factor of 3 or more, 3 to 5. And we even see that Tripleclouds performed similarly well as the full ICA experiment, which really means that it eliminated the vast majority of errors stemming from unresolved cloud structure in this case. So having this one extra region to represent the cloud was really helpful in this case to eliminate the vast majority of biases. But what remains is really the classic horizontal photon transport, which you cannot properly eliminate with this solver. As a next step, I then tested the sensitivity of the solver to the assumed form of liquid water content distribution. And so this is the same graph as before, except that I used 3 different assumptions for cloud condensate distribution, Gaussian gamma and log normal. And we see there is clearly some sensitivity to the assumed form of distribution. Log normal did not work so well in this case, so we have to be careful which distribution we choose. But overall, the solution remained more accurate than the traditional GCM calculation in all these experiments, regardless of the exact assumption of distribution. And so in the next step, I asked the question, how does the method works for various cloud types, and how to configure Tripleclouds for various cloud types. And so in addition to the shallow cumulus cloud field case study that we've analyzed, and is again visualized here on the left, I have also analyzed cases of stratocumulus, cirrus, and cumulonimbus. And I have repeated these baseline experiments with the global estimate of fractions of deviation, with these various distribution assumptions. And they work relatively well for cumulonimbus, but they completely failed for stratocumulus and cirrus. And so I had to think how to optimize the treatment of these two cases. And what I'm visualizing here at the bottom are the vertical profiles of fractional standard deviation. So these profiles are derived directly from these high-resolution cloud scenes that we see here. And for comparison, I'm plotting the global estimate. So the mean value is this vertical black line, 0.75. And then this uncertainty is the gray shaded area. Not so well seen. Yeah, the first thing that we see, obviously, that cloud horizontal inhomogeneity strongly depends on cloud type. So these profiles are intrinsically different from cloud case to cloud case. And if we focus on shallow cumulus first, we see that the inhomogeneity is strongly dependent on the height within the cloud layer. It's unfortunately not constant, but it predominantly lies within this range of global estimate. And this is also the explanation why this simple Tripleclouds experiment using the global estimate worked quite well for shallow cumulus. For stratocumulus, it turned out that, radiatively important is this upper part of the cloud. So if you look at the cloud fraction profile, simply most of the cloud was concentrated in the region around 1 kilometer height, and here the actual inhomogeneity of this scene is lower than a global estimate. Whereas for cirrus cloud, the opposite was the case. Cirrus was extremely heterogeneous with very high values of inhomogeneity. And so let's now take a look how we have configured how we have optimized these two cases. So the problem with overcast cloud scenarios or overcast grid box in general is that they do not contain cloud edges, which contribute to increased variability. So this mixing of cloudy and cloud-free air at the edges of clouds tends to decrease the mean water content at cloud edges. So cloud edges are optically thinner, that's what we already said. But at the same time, it also acts to increase the spread of liquid water content, to increase the variance of liquid water content at cloud edges. So cloud edges are not only optically thinner, they're also more variable. And therefore, a grid box which does not contain any cloud edges will be more homogeneous. There are various parameterizations which consider this cloud edge effect and which consider dependence of cloud inhomogeneity on cloud fraction, such as that of Bautel et al. 2014. And when I have employed this parameterization in the Tripleclouds, the radiative biases were largely eliminated again. This is this orange experiment. I'm showing here the Nate surface flux bias as an example. So radiative fluxes of the surface are largely dominated by the solar component, and so are the biases. And in this way, we could also configure Tripleclouds in a way that it worked well for these overcast cloud scenarios. In case of extremely heterogeneous cirrus, it turned out that the ice water content distributions are highly skewed. Highly skewed means there were many small ice crystals and only a few very large ice crystals. So distribution almost had like a delta peak at this small ice crystal size, and then they had like really, really long tails due to a few or rarely occurring large ice crystals. And in this case, it's not so clever to geometrically split layer cloudiness into two equal parts, but it makes more sense to allocate larger amount of layer cloudiness to the optically thin region where we would place this many tiny little ice crystals. And so this graph shows the error in the cloud layer as a function of split percentile. So our default configuration with a split percentile was using split percentile of 50, where we have divided layer cloudiness into two equal halves. And then I have gradually increased the split percentile. So that value of 70, for example, means that we allocate 70% of layer cloudiness to the optically thin region. And I've performed various experiments in the solar part of the spectrum, and we see that they generally have a minimum here at values of between 85 and 90. So the solution in this case was really to allocate a larger portion of the cloud to the optically thinner region. No matter which kind of improved parameterizations of cloud inhomogeneity, of fractional deviation I used, I could not eliminate this problem unless I started seriously playing around with split percentile. And so the conclusion of the second part would be that Tripleclouds radiation scheme is an efficient approach to reduce cloud radiative biases, which stem from unresolved cloud structure in coarse-resolution atmospheric models, if you configure it properly at least. But the optimal Tripleclouds configuration, which minimizes the radiative bias, essentially depends on cloud type, because the nature of cloud horizontal inhomogeneity strongly depends on cloud type, and this supports the use of cloud regime-dependent methodologies in atmospheric models. And that's basically it. So thanks. And if you have any questions, I'm happy to answer.
I was wondering, when you said like the traditional GCM approximation, do you include a clear and cloudy column, or you just have one column mixing all those?
So traditional, for me is having cloudy and clear sky at the given height within a single column. So traditional GCM would be, so in traditional GCM, you can imagine this entire scene would be within a single column, and then at each height I have the information about cloud fraction, so I have cloudy part of the grid box and clear sky part of the grid box.
And you said that's on the regional scale?
So this is actually how clouds are represented in regional models, for sure. In global climate models, clouds are currently better represented, mostly. It depends on the GCM, of course. I would be happy and interested to talk how exactly is radiation treated in the GISS model, but many US models use another type of radiation solver called the Monte Carlo ICA, Monte Carlo Integration of Independent Column Approximation, which is a bit different method. It's a method where you use a stochastic cloud generator to generate subgrid cloud structure, and then you compute this one-dimensional independent column solution. But because this is still too computationally expensive for use in GCMs, you have to further, optimize it, make it faster. And what you do is then you do not compute the 1D solution in each individual column, but you randomly sample columns, and you also randomly sample spectral intervals. Spectral integration is something that we didn't really discuss here, so I was really dealing with these errors stemming from cloud structure. But Monte Carlo ICA is an alternative approach, and it would be interesting to compare, maybe Monte Carlo ICA and Tripleclouds in terms of accuracy and computational efficiency.
I think they mostly gave up on the spectral sampling. I think that didn't pay off or something. That's my understanding. We have a very, very crude, and I have nothing to do with it.
Spectrum.
But the GISS GCM, we have a grid cell is either cloudy or clear each layer, and, with a random, Monte Carlo approach. It's pretty old fashioned. I don't think anyone else does it.
Okay. So what people often do when they have such solver to account for cloud inhomogeneity, at least in a simple way, they scale cloud optical thickness. This is a so-called scaling factor method. So if you calculate the radiation in such homogeneous layers, you get really large biases in GCMs, and people have found simple ways to deal with this. And one simple way is, simply scale optical thickness with a constant scaling factor, and then use this effective optical thickness as an input to radiation scheme. Another issue that I did not really discuss is, how to optimize the vertical structure of the clouds. So here I'm using this maximum overlap assumption for adjacent cloudy layers, but what a few GCMs imply is the exponential random overlap. So this is important in case of strong, in case where you have strong vertical wind shear, and then the adjacent layers are shifted a little bit, and this is something that I could upgrade also in the next step. But yeah.
So in regards to the cloud types, if you were able to tune the parameterization to a specific cloud type, would it be the fractional standard deviation? Is that the tuning parameter you would use?
Well, there are several tuning parameters. So here I have played with all of them, but obviously, yeah, so one decision that you have to make is really what's the degree of inhomogeneity that you will introduce into the scheme, but then also the shape of the distribution, Gaussian, gamma, log normal, and other distributions. Usually they are Gaussian or they are, gamma or log normal. Gaussian is only the theoretical one, but in these boundary layer clouds, usually liquid water content would be distributed either according to a gamma or log normal distribution. But then it's also really the shape of this distribution, like the skewness, as we have seen. So, also log normal distribution can have very different forms. And so depending on the form of this distribution, you have to further play with the split percentile, for example. So there are, in general, multiple combinations of these parameters, which would give you good solutions. And it's tricky to play with that. It was also, sometimes quite sensitive. As you can see here, I'm showing the two results, Tripleclouds. So for Tripleclouds, so here I was using the global estimate, and it worked really bad. So it even resulted in a larger bias than the conventional GCM calculation, which means that if you introduce wrong degree of inhomogeneity in the Triplecloud solver, like too strong or too weak, you can even end up with the result which is worse than the conventional plane parallel solver. And so you have to be careful when you set up these parameters. When I think about which direction I want to go next, I'm not sure if I would be really developing Tripleclouds as a next step. I would perhaps rather work on better characterization of this cloud inhomogeneity for various cloud types. There is still a lot of improvement in this direction, and this is then something that can be used for all GCMs. And this is, in a recent study that we had with Greg and Robert and Andy, we have evaluated 12 SIM6 models, and they all had substantial biases in clouds and radiation for this boundary layer cloud. So I think it would be maybe most helpful if we would further develop these parameters describing cloud inhomogeneity, which is this characterization.
And how did you define the cloud types?
How did I have simply picked this for cloud cases, which I considered as being cumulus, stratocumulus, cirrus, and cumulonimbus.
They're LES case studies, right?
Yeah.
So this is the LES, UCLA LES, cumulus and stratocumulus. This series is generated with a stochastic cloud model called CloudGIN of Hogan and Ku. So this is a bit different type of model, which allows for a quick generation of cirrus clouds. It's based on some radar measurements in England. So, and then this is actually the Goddard cumulus ensemble model, which produces cumulonimbus. And I have intentionally picked these cloud field case studies so that they were more or less maximally overlapped. So I searched for the situations with weak vertical wind shear so that I could address them with my version of the Triplecloud solver. And so I could really focus on cloud inhomogeneity problem and eliminate a problem which I have with vertical cloud structures. Yeah. Yeah.
So why does ICA work as well as Tripleclouds? It seems like that was a result you found. The error for ICA was comparable or so much.
Here?
Yep. Yeah. So are you taking into account horizontal fluxes in ICA, or I mean, I thought you weren't.
No. So the so I have performed this ICA calculation on this highly resolved LES cloud field, on the original LES cloud field. So here really lots of information was passed to the solver. We have like, domain size of 50 times 50 kilometers with horizontal grid spacing of 100 meters, which means that I ended up with 1,000 LES pixels. And so way more accurate than it's illustrated here. And I have run the 1D solver on this cloud field. And then, surprisingly, as you can see, sometimes Tripleclouds worked even better than the ICA. And this was really surprising. But a simple explanation for this is, if I go back, that in this Triplecloud solver, you still...
just press
Snooze.
In this Triplecloud radiation scheme, you consider a little bit of horizontal photon transport, not the full amount, but you have effective treatment of a partial component of horizontal photon flow as well, because you kind of scatter radiation a bit from region to region. And so in this case, it even worked better than the full ICA. So, I mean, at least in the solar part of the spectrum, thermal. During daytime, the ICA was better. So physically relevant quantities are of course thermal radiation during nighttime, and then the total effect during daytime, they were close in this case.
ICA has got to be much more expensive computation, right?
Yeah. Mm-hmm.
So I'm Zhang Haijin. I have a question. And for compared to the homogeneous clouds, or for the how much more time is your scheme required? It's 3 times more, or about 4 times more computation time?
Yeah. So when I add an extra cloudy region, I have to add extra component of radiative fluxes, which I'm able to steer to this cloudy region. So I need to add 1 additional component of direct radiation and 2 additional components of diffuse radiation at each vertical layer when I incorporate a new cloudy region into this solver. And then it depends on the number of vertical layers that you have. So when you couple radiative fluxes on this Triplecloud model and you formulate the overlap rules, then you have to build a matrix system. And in my case, the solver is quite computationally efficient because I only employ pairwise overlap. So when you do the overlap, there are various ways how you assume this, how you make this overlap assumption. And I'm always employing pairwise overlap. So I'm looking at 2 consecutive layers. And in this way, I end up with a matrix which does not have so many elements, so I can properly formulate this matrix with only a few diagonals with non-zero elements, and then I can really efficiently solve this. But it depends on the number of vertical layers that you have, the additional computational cost.
Okay, so that means it requires at least 3 times of time compared to the traditional GCM 1-point PDF.
I didn't hear.
3 times is
Yeah.
It's at least, yeah, 3 times more. Yeah. Also, have you estimated the uncertainty in the transmission for Yeah, for the total transmission, have you estimated that?
You mean
The cloud transmission, have you what's the uncertainty for that, and what or errors? How much percent of the error in transmission
I
or
haven't
transmittance?
estimated this. So here, what I was doing. So this scheme shows transmission of radiation to adjacent cloudy layers, and I have simply divided these fluxes really in accordance with the sizes of individual regions. The question is also, is it really correct to do this? The recent work of Robin Hogan, the paper 2019, they when they improved their original version of Tripleclouds, they also discuss more precisely how to split this, how to really steer these fluxes between these layers, and this could be also a little bit further optimized in the next step. But I'm not sure if you asked this.
I think it's asking what your bias was in the different metric than you showed us. Right.
Yeah, I was always diagnosing atmospheric heating rates and net surface fluxes, the two quantities that I have to compute in a weather climate model. And so this is heating rates in the cloud layer, and net surface flux is the difference between upward and downward radiation at the surface, and it's proportional to surface heating. And I was always diagnosing this throughout my work. Transmission is only one process. Yeah.
Do we have any more questions in the room or any more online? No? Okay, then can we give another round of applause for Nina? Thank you so much. So for those of you who are online, just a reminder that we recorded this seminar and we'll be posting it on the GISS YouTube channel.